All right, so as we were saying where we left off from last week, ASHRAE 62.1 is the de facto ventilation standard for the country. That feeds into the International Mechanical Code. For the most part, they cut and paste the language in there. And then in most cases, that also feeds into the local mechanical and ventilation codes. City of Chicago is a little different. Wisconsin, the state, is a little different. But pretty much everywhere else is following 62.1 or the IMC. The good news is that's been written into the code since 2004 on ASHRAE side and 2006 for IMC, specifically spelling out that CO2-based demand control ventilation is permitted by code and allows you to operate the ventilation system lower than the otherwise prescribed data that's in the tables there. So it allows you to go below the code minimum if you have CO2 sensor systems. Prior to that, I was running around with a little commentary to the IMC that stated this, and that was using that to get that approved for some jobs, but I didn't even have this till 2004. So from 2000 to 2004, it's pretty hard to convince people to do CO2 systems. Now it's super easy. It's allowed by every single mechanical code. I can't think of one code in one state that doesn't allow it at all, although I'm sure someone will type one in for me. City of Chicago is a little bit different than the rest of the state or even the rest of the Midwest or the rest of the country. City of Chicago has been doing it for a couple years longer in the code than other places. The difference, though, is that instead of having a differential allowance for parts per million between the inside and outside, say like 700 parts per million higher than the outside, so if you have 450 outside levels, you have 1150 for an inside set point, City of Chicago says, no, we're just going to do a flat 1,000 parts per million. The reason for that is because at the time they wrote this into their code in 2003, it wasn't spelled out specifically in the ASHRAE standard, so they went with 1,000 parts per million because it's a little more conservative and a little more historical. But the point is you can do it in the city of Chicago. You can't get quite as good of energy savings as you can in the suburbs, but it is definitely allowed, and the savings are still pretty big. Wisconsin, I know I got a lot of guys from Wisconsin on the webinar. Wisconsin's a totally different animal. We've had a lot of trouble using CO2 sensors in the state before because it wasn't specifically spelled out that it was allowed in the mechanical code. On the flip side, it wasn't prohibited either, so you just kind of really had to have a good engineering case to present to the state to do it. And in the ventilation code for Wisconsin, it does specifically state that if you can demonstrate an engineered system, you're allowed to provide other ventilation rates than what's spelled out in the code. So that is written in there, so you do have a legal way to do it, but you have to have an engineering case to present to the state to do that. Additionally, and the bigger issue in Wisconsin is, Wisconsin already has pretty much the lowest outdoor air ventilation rate for code purposes than anywhere I can think of in the entire country. Most places for say like an office building, on average, depending on the density of people, requiring 15, 17, 20 CFM per person is pretty normal. Wisconsin requires 7.5 CFM per person for all building types and occupancies. So it's already really, really low. It's basically less than half of the ventilation rate that everywhere else has. So the benefit of using DCV is not as great in Wisconsin. I'm not saying there's no benefit. I'm just saying the payback's going to be a little longer because the code baseline is a little bit lower already. But you can do it. Not only is it allowed by all the mechanical codes now, demand control ventilation is actually required in some cases by the energy code. Right? So ASHRAE 90.1 is our energy standard for the country. It feeds into the International Energy Conservation Code, IECC, and that feeds into typically the local codes, and sometimes they make tweaks to it and stuff like that. But for the most part, they adopt most of it as is. So specifically in well over 20 states now, IECC 2012 is the code, and then in, it would be 18 states, 2009 is the code. So almost every state is on a 2009 or 2012 version. There's a few holdouts like Wyoming who doesn't have codes, but that's another story. The 2009 version says that if you have a population density in a space that is 40 people per 1,000 square foot or denser, you are required by code to have demand control ventilation systems in that space, reducing the ventilation error when people don't show up. If you're on the newer code 2012, like Illinois is on, and very soon Minnesota will be on that here in the Midwest in June, then it changes from 40 people per 1,000 square foot to 25 people per 1,000 square feet. That pretty much includes conference rooms, classrooms, movie theaters, auditoriums, sporting venues, all these places that have a lot of people. You pretty much have to do CO2 sensors by law. You're kind of required to do it. There's a few exceptions, as you can see on the bottom there, but for most spaces, those exceptions don't apply. All right, so here's kind of where the action is at. This is one of my favorite slides of any presentation. So I'm going to try to use this little pen thing and see if it works here. So what we have down the bottom here is midnight to midnight of a typical day, and up the vertical axis is 0% to 100% of the code required air. So it's not 100% of the mixed air damper, it's 100% of the code air. The damper itself for an economizer day could go, way, way, way more open, right? But right here at the top, that's my code ventilation rate. So on a normal day, we go occupied at like whatever, 7 a.m. or something like that. Everybody shows up the building. We go to the occupied ventilation mode. We do everything inside this green box. That's how much ventilation air we bring. And then at the end of the day, 6, 7 o'clock at night, whatever it is, we shut the ventilation back down. Now, as we already said, a lot of times we're also opening that ventilation air in the middle of the night whenever we have a heating cooling call, but that's a separate discussion, right? So now what happens on a DCV building is we follow this purple curve. So we basically say, well, you know what? Everybody didn't show up at 7 o'clock. Some people trickled in a little bit later, 7:30, 8, 8:30, whenever. By 9 o'clock, most people made it to work, right? By whatever, 11 o'clock, some people start cutting out early for lunch. Then a lot of them go out to lunch. That's that dip, that V there, right? Most make it back from lunch, although some don't bother because they don't have to. And then by whatever, 3 o'clock in the afternoon, everybody cuts out early for golf time, right? That's a typical building. This is like every office building that we go to. We have this, what we call two-hump profile. It's very indicative of all these types of buildings. And everything in the green there is what I would have had to do if I didn't have DCV for code required ventilation. The purple is what I'm going to do once I have a CO2 sensor. I basically recognize that people aren't all there, and they're coming and going and things like that. So it's a very predictable pattern. This particular one that was on the screen is from a building down in Florida, but this is the same pattern I've had on every single office building that I've ever done. There's also federal study data that shows that same two-hump profile for office buildings. It's very predictable, and the first hump's always taller than the second hump. If you got a restaurant situation, you get the 3 humps, breakfast, lunch, and dinner, and you get that little, bonus hump afterwards when you get all the people that don't like crowds going there, right? So after lunch, you got these people that come in and go to lunch at 1, 2 o'clock in the afternoon or whatever, right? When you're at lunch in the daytime over here in the big V, somebody else is at the office, and then you kind of flip-flop. So that happens. The point is that these patterns for different building types, school, office, restaurant, etc., are very predictable for buildings, and hence because they're predictable, we can easily give people a good guesstimate of how much energy can be saved on a given project if we know what kind of building they have. These are typicals, averages, if you will, from various projects. Most of these are from projects in the late 90s, early 2000s, but it's the same data now. The top line across the top, that would be your code required ventilation air if you did not have DCV. You'd be bringing that much air in, 100% of your code air, right? Then what happens on these, oops, sorry about that. My screen just decided to fall asleep. There we go. What happens on these DCV jobs is the orange bar there. It shows you what we really end up ventilating for when we actually track the people. So for an office building, I'm saving 30%, 25, 30% of my required ventilation air, right? And that's pretty believable based on the two-hump profile I just saw you. Retail, it's huge. I'm saving like 90% of my ventilation air. That's ventilation air I don't have to pay to heat, cool, humidify, dehumidify, filter, whatever I'm doing. So it's a lot of savings there. And the reason for that is these buildings are designed for some peak occupancy, whatever, Christmas Eve, Black Friday, whatever it is. But most of the time, it's not that populated. There's only so many people that are shopping at a Walmart at 3 a.m. I mean, there's people there, don't get me wrong, but there's not a lot of them. And the ones that are there don't need ventilation air. They're already crazy. Restaurants, same kind of thing. I'm getting, 85, 90% reduction on those guys as well. And by the way, this is the dining room portion of the restaurant for this chart, not the kitchen. Kitchen's a separate discussion we'll talk about later. And that's because these are designed for, whatever, Saturday night dinner crowd. But how many people are eating lunch at, 3 o'clock in the afternoon on a Tuesday or at 10:15 in the morning on a Thursday, right? So there's lots of hours of non-peak occupancy. And then we got schools, which is one of the more interesting ones. There's lots of stuff happening with the school. Right? For one, you don't have the summer hours. This isn't really indicative of that at all. The big thing is the classroom might be designed for 35 people. Maybe you only got 27 kids, right? So that's whatever, 5, 6, 7, 8 kids all year long I don't have to ventilate for, right? Just for starters. And the other thing is every single room in the school has to be designed for the peak ventilation rate. for the peak occupancy of people. But all the kids can't be in every single room to max occupancy at all times. When my kid leaves the classroom and she goes to the gymnasium, there's nobody in the classroom anymore, right? And when she goes from the gym back to the classroom, the gym could be empty. And then outside for recess, and then to the lunchroom, and then to the classroom, and then to the art room. They're moving all over the building. Every room is designed for the peak, but each person can only be in one spot at one time. So these places that have these four main types of places, and a few others I'll show you in a little bit, that have a lot of people, large quantity of people coming and going and moving around, those are really the best ones for DCV, because DCV tracks people. That's really what it does. There's all kinds of weird things popping up on my screen. All right, let's do a poll question here. We'll start off with a nice easy one. So true or false? Upgrading to a RTU model upgrading to an RTU model labeled high efficiency is the only way to save energy on a rooftop unit. This is the soft, easy one that hopefully you guys all get, and then we'll make the other ones a little harder. And while you guys are answering that, I'll see if you typed any questions in for me. Boris asked a great question. What is the ventilation requirement during unoccupied mode? During the unoccupied scenario, when nobody's at the building, you are allowed to ventilate down to 0%. So you shut all the ventilation dampers completely. And then when the building goes occupied, say whatever, 7 a.m., then you need to ventilate for the code-required square footage portion, and then you need to also ventilate for the code-required per person portion, assuming the people are there and breathing and recognized by the CO2 sensor. But at nighttime, you can shut it all the way down to 0, assuming the building's unoccupied at night, obviously. If you're a 911 center, then there is no unoccupied time. Let's see. Jeff asks, is the required DCV enforced for partial renovation of existing space or building that isn't equipped for it, doesn't have DDC? It's a great question, Jeff. So the energy codes, I don't have the code on my computer to bring it up right now, but the energy codes are not a new construction thing. The energy codes, specifically the IECC, spells out in there that this applies not only to new construction, but to also to renovations, alterations, additions, replacements, and repairs, right? So as soon as you change something in the building, you got to bring that thing up to code. Now, you don't have to go back to every single building you ever did and all of a sudden magically make them all comply with the current code. But if you are going to install a new rooftop unit or a new boiler system or add new windows or whatever, those things you're installing and the things that relate to them and connect to them, those have to be updated to the current code. So if you change out a rooftop unit and you put a new one in, and let's say the rooftop serves a classroom and it's more dense than 25 people per 1,000 square feet, then you are required to add a CO2 sensor to that classroom on that renovation project. Let's see, let's go back to our poll question and close that out. So you guys did really good on that. 99% of you said that is false, right? So obviously there are ways to be more efficient on a rooftop unit other than just buying the one that says high efficiency on the tag, right? And some of those things are things we're talking about. Programmable stats, demand ventilation, ERVs, etc. So that's good. Dan asked a good question, and hardly anybody ever asked that. What does the baseline represent? The baseline in this case was just randomly shown at 30%, but what it is the square footage portion of the code, right? The 0.06 CFM per square foot. Now, hardly anybody ever notices it, and I've used this chart with well over 5,000 people before, presentation-wise, and really, in reality, Dan, I probably should update it just to show a little better, but these sections right here, oops, there we go, now you can see it. These sections right here really could go down to 0. The reason it was shown like this is because what should happen is they should go down to 0, right? The green curve should drop all the way down to the bottom at 0. But what happens in a real building, like I said, is it goes up and down on heating and cooling call. So we left it at 30 on the drawing to represent what happens in a real building, right, of it being either 100% or 0% of ventilation air, depending on whether the stat's calling for heating or cooling or not, right? But that's what that was for. Gary's asking what parts per million you are seeing for non-Chicago projects. I'm assuming you're talking about a set point, and a set point is very commonly set in my world at 1150, because most of the time I take a measurement outside and I'm around 450, and 700 above the 450 is 1150 set point. Now, if you're asking about what do I just see in buildings when I walk in with a CO2 meter, unrelated to the building having DCV, it's all over the board. I just did a presentation last week at IIT. We started off at 529 CFM in the classroom. We ended the class at 1,632, I think it was, 1,631 parts per million. It's all over the board. And it does make a difference whether it's an economizer mode or not. That kind of throws it off a little bit. But if you take the readings with a handheld CO2 meter in the dead of summer or dead of winter, then you'll get a good idea of seeing whether the building's over or under ventilated. And I'll show you some stuff on that in a little bit. Marty also mentions base ventilation rates should address minimum building pressurization requirements. That is true, although I would assume that if the building's unoccupied, in most projects you're also turning off all the exhaust fans and all that kind of stuff as well. And Gary also says the same thing as Marty there, so you guys are on the same page. So usually all that stuff can be shut off completely, but if you are running exhaust in the nighttime, then you would have to also deal with that. All right, let's get back over here to the slides. Okay, there we go. All right, so there's just some typical samples from around the building, just around the country, excuse me. So you can see that the idea is that these paybacks are pretty fast, and they're even a little bit faster now. These paybacks on this screen were done in 2003, and the cost of CO2 sensors actually has come down a little bit, not a ton, but it's a little bit. But labor's gone up, so it's probably a bit of a wash. You can certainly find tons of studies out there that show crazy savings, $130,000 for 6 months in this case. And that's fine, but everybody's building's not that big, so it's not super meaningful. I'd much rather do simple calculations for that building, and I'll show you some of those simple calcs in a little bit. There's lots of buildings that are using this. I don't need to go through the list anymore because there's literally thousands and thousands of buildings. But back in 2000, it was pretty niche-y, and these are some of the big early adopters that adopted it in the 90s. So I'm not going to go through all of those just because of time reasons, but there was a bunch of people that jumped on real early on in the late 90s at different high-profile type buildings. Wisconsin, like I said, has become much more accepting. The utility company's been pushing for it. The energy code's been requiring it, so it's kind of forced the mechanical department to look at it a little bit differently. And they have been accepting the products, although, like I said, you do have to kind of prove things out. This was a case study done by the utility company for feasibility on it. This was a big box retail place. They considered it one giant zone, if you will, even though it was multiple rooftops. And they were able to get an 8-month payback on it, including the utility rebate at the time. All right, so this chart here on this page is really useful. I've been using it for, I don't even know, 15 years. And it does a really good job of illustrating what systems this is a good idea on. This is for demand control ventilation specifically with CO2 sensors. There are other forms of DCV, but this is a chart specifically for CO2 sensors. So what this chart means is if it's an A, it's a good idea. If it's a C, it's a bad idea. If it's a B, we probably need to talk about it. So ones that are good ideas are some of the ones we talked about, right? Classrooms, music rooms, libraries, auditoriums. They all have a lot of people coming and going, right? Sporting arenas, any type of indoor sporting venues, probably a good candidate. If you have an ice arena, you got to be a little bit careful because of the Zamboni situation. But we program override modes in for the Zamboni, and it's very doable to do the DCV for the spectator portion. Office buildings are great candidates. Retail sales floors are good. We generally stay away from the medical stuff because there's pressurization issues and disease control and all that. But sometimes we'll do it in the lobbies and open areas and waiting rooms and cafeteria type stuff sometimes. Hotels are fantastic candidates, not the bedroom areas specifically, not the rooms, but all the conference spaces, the meeting rooms, conferences, the lobby, and all that stuff are fantastic. Gymnasiums are good candidates. The ballrooms and the discos, I suppose the younger crowd can call that a nightclub, but you can get the idea. Those are all really good candidates. The ones that are really bad either have some kind of chemical thing going on, or they don't have people coming and going, right? So a guard station at a prison, people really shouldn't be leaving that unoccupied, right? So there's always supposed to be fully occupied with guards, so that's not a good candidate, right? Commercial dry cleaners, we're not ventilating that space because of the two guys breathing back there. We're ventilating it because of all the chemicals that they have to inhale. So whether there's one or two guys in the back, it shouldn't make a difference on my ventilation rate, all right? Locker rooms, they already stink absolutely horrifically. Hockey gear shoved in there for 3 months. You do not want to cut the ventilation air back in a locker room. It'll smell even worse. Kitchens are definitely an issue. You can do DCV in kitchens for the exhaust systems. You just don't use CO2 sensors for it. There are DCV systems specifically for kitchen hoods and stoves, and typically it's some kind of infrared/thermal sensor that they use in those cases. Parking garages and vehicle maintenance bays, same thing. We can do DCV, and it's very common. We just don't do CO2 DCV. We do CO, carbon monoxide, because that's what the vehicles are, quote-unquote, exhaling, if you will. And if you have a diesel place, then we do NO2 in addition to the CO, but not CO2 sensors. Pet shops, for the same reason as locker rooms, they already smell bad. Manufacturing, you really got to kind of tell us what you're doing, otherwise we can't say yes or no to that. Warehouses are bad candidates because there's like 100,000 square feet and 5 employees. I couldn't sense you breathing if I wanted to. Like I said, we stay away from all the medical stuff, operating rooms and all that. We stay away from autopsy rooms, and mortuaries are bad. Hopefully you know why. I can't find any CO2 in there. Swimming pools, because of the chlorine, we don't want to mess around with the ventilation right there. Plus, we usually need it to help out with some of the dehumidification needs. So those are all no's on the C's. The B's are the maybes, right? So training shops, laboratories, well, what are you doing? The dining room at a restaurant, well, the dining room we can do DCV on, absolutely. The problem is a lot of engineers, or non-engineers for that matter, design the dining room ventilation air to also be a portion of the makeup air unit for the exhaust fan. In my world, the kitchen should be isolated, and the exhaust fan should have its own dedicated makeup air unit sized for the exhaust fan. And if that happens, then I can do the dining room with DCV. If that doesn't happen, and you're expecting me to steal air out of the dining room to make up the hood, then I can't do DCV, right? The bars were on there and cocktail lounges at the time because of smoking. Smoking is a non-issue in most states, so now you can do it in those spaces. All these specialty shops are all maybes because you got to tell me what kind of chemical thing you have going on, if any. And if you don't, then you're fine. That sort of thing. Bedrooms are not good candidates, whether it's a dormitory or a hotel or whatever, because there's just not enough people in a densely occupied space. So hopefully that helps you guys out in determining which spaces you can do this in and have it make a lot of sense. Bruce asked if we can get copies of the chart. Yes. If there's anything you want, send me a note on it. I hate to have to do it that way, but it'll be easier if you just send me an email on it because I'm in the middle of presenting it, so I don't want to start trying to take notes from people when I'm presenting it, just because it'd be too hard. Back to Marty's question about, I think it was Marty that asked about inside levels that we see. For most places, a good target is going to be like 1100-ish, 1150 for a typical ventilation rate. Like I said, most office buildings for typical density are looking for about 17 CFM per person per the current code, so that's kind of right in that range. But as you can see down the right hand of the side, the CFM per person fluctuates with the CO2. They're directly related to each other. In fact, the CFM per person that's in the codes, I don't remember if I said this last week or not, but the CFM per person that's in the codes, that number, those numbers in the tables were originally backwards calculated from CO2 study data back in the 1980s. That's where those numbers had evolved from. So it's not a new idea at all. But you can go to a building with a handheld CO2 meter and have a couple of those meters, and they're pretty useful. And I can walk in somewhere and see it's 500-600 parts per million. Unless it's an economizer day, I know they're overventilating, right? And they're wasting energy. If I walk in there and it's 14, 15, 1600, I know they're underventilating. And it's, probably smelly and stuffy in there. And then if it's up in the 2000s, then it's probably at the point where people don't even feel all that great. I mean, they're not sick, but they probably feel groggy and stuff like that. All right, so CO2 is not a new idea. This has been around forever. I'm not going to read all this to you. Just know that literally it's been around forever, at least as long as all of us have been alive. The 1,000 parts per million that Chicago uses as a set point, that's not a new number either. A lot of the old documents used to say 10 parts in 10,000, which, oh, by the way, is 1,000 parts per million, same number, right? So it's been around for quite some time. There's a pretty long history of it being spelled out in certain codes and standards and handbooks. And then, like I said, 1989, the ventilation rates were really backwards calculated from the CO2 data for ASHRAE 62 when it came out in 1989. And then in 2004, it became really code acceptable, spelled out as being code acceptable. Reason for popularity increase, obviously the mechanical codes allow it, the energy codes sometimes require it. The sensor costs have gone down tremendously. I stopped my chart at this point because it's pretty much leveled off for the past 10 years. But I can get a CO2 sensor for like $200. It's not that expensive. I'm probably exaggerating. It's probably like $250, right? But still, it's pretty inexpensive relative to what it was back in the day, if you will. The other thing that's been really nice is I don't have to calibrate CO2 sensors anymore. I spent a good portion of the early 2000s calibrating CO2 sensors every year, and that was a pain in the you-know-what. Going up to each sensor, hooking up a can of gas to it, running the gas through there, pushing the button at the right time, hoping I zeroed it out the right way. Then I'd have to worry about somebody else coming along and pushing the button with no can of gas connected to it, and they messed up my reading. The good news is all that's gone away. All of the commercial grade CO2 sensors have gotten rid of the calibration option. You cannot calibrate them anymore. You can get industrial ones, and those can be calibrated and should be. But for the commercial use ones, offices and schools and all of that, there's no calibration allowed on them anymore. They took the button off because people were pressing it at the wrong time. Instead, what they do is they give you a 15-year design life for this sensor, so it should not go out of calibration. And most of them give you a 10-year guarantee on the calibration. The way they do that, and there's two manufacturers that make these CO2 engines, if you will, and they put them in everybody else's plastic housing with their logo, and custom brand them and all that. There's two people making this engine, and basically what they have is this thing called automatic baseline calibration. As long as your building goes unoccupied for at least 4 hours a week, which is almost every building in the country, right? At least 4 hours a week, no one's there. That's enough time for most buildings for the outdoor air to seep in all the cracks and crevices and the CO2 levels from inside and outside to neutralize with each other. And the outside air levels are always the same number. Now, sure, they change over the decades, if you will, right? But on a day-to-day basis, it's always the same number outside of parts per million of CO2. So basically, it self-calibrates itself to the outside air levels every single night. That's basically how this works. So there's 3 sensors hanging on the wall over 5 days. Basically, you can see they tweak themselves out to basically be the same reading. There's a couple sensors all over 2 weeks doing the same kind of thing. They start out a little bit drifted apart from each other by 200 parts per million, and they eventually, maybe 150, then they drift themselves to being basically the exact same number. And there's 3 sensors over the course of like 3 years doing the same thing, holding their calibration level. So it's pretty easy to do. If you have a sensor that goes out of calibration, you literally return it under warranty if it's within 10 years and they give you a new one. I think I've done it like 8 times, which sounds like a lot, but I've literally done thousands of CO2 sensors, so it's really not that much. There's lots of tools you can use to calculate savings. I happen to like this one a lot for a couple of reasons. This is the Honeywell tool. I don't work for Honeywell or anything like that. They just have nice free things for me to use. I like this one because it takes into account thermostats, economizers, and DCV, and the interaction of those. Right, so if I give you a calculation and said your thermostat's going to save this much because it's programmable, and your economizer is going to save that, and your DCV is going to save that, and I added them all up, and I told you you're going to save 82% of your energy, you'd be like, what the heck? That doesn't sound right. Well, yeah, it's not right, because if your stat starts making your rooftop be unoccupied half the time, well, now the CO2 sensor is not going to, be doing as much work for me, and the economizer is not going to be used as much, blah, blah, blah. So they have to be interacting with each other. So the way this works is, I won't go through the whole thing, but you put in your building type, the efficiency of your rooftop, the square footage of it, the basic occupancy, are you a school, office, whatever, and then your utility costs. It takes less than 5 minutes total for this whole entire thing. And then you press calculate, and you get a screen like this, and you can also run little reports and all that. In this case, it shows the base case, and it was basically telling us, like my spotlighter thing, that my total utility cost was almost $6,000. And if I put a setback thermostat on there, I was able to save $1,700, which is 28%. If I put a setback stat on there with a dry bulb economizer, I was saving 31%. If I did differential enthalpy, I was saving 34%. If I did DCV, differential enthalpy, and a programmable thermostat, then I could save 36% way over here at the end, $2,100. So there's a bit to be had when you start combining all of these things. And you could do the example without programmable stats too, right, and back that out and see what the DCV savings is. But for this building, I think when I did it, it was about $1,000. Actually, it was $900 and some dollars when I did just the DCV with no programmable stat, right? So $900. The sensor probably costs $250, and then you have to pay somebody to wire it, install it, and commission it, that sort of thing. Your economizer already has an input waiting for it. So let's just say it takes someone half a day to install it and wire it. And let's say they charge $100 an hour because that makes the math easy for me. That's $400. Let's say they charge you $300 for the sensor. It's $700. So I should be able to pay back in under a year because it was saving me $900 a year. The bigger the rooftop, the faster the savings. The more CFM of outside air, the faster the savings. The more people that are designed for but not showing up, the faster the savings, that sort of thing. There are some rebates that are available as well. Look at the questions real quick. There are a few. Jonathan asks, what is a typical DCV control strategy for multi-zone systems? All right, so our DCV zones typically separate into single-zone systems, and the damper homogeneous requires a okay, so for multi-zone systems, we do a little bit differently. On a single zone, we simply wire the CO2 sensor to the economizer controller that has an input waiting for it, and we set two different minimums, one for CO2 mode, which is basically what to take care of my square footage portion, and then one for square footage and people, which really becomes my maximum, right? And that's really straightforward and easy to do. When you have a zoning system, it's kind of like some of the examples I showed last week. I need to know if people are moving from one room to the next room. I can't just monitor one sensor, right? And I certainly can't put one in the return duct, because then I'm going to get an average of all the zones. When you have one conference room and 10 offices surrounding it with 10 employees, if they're all in their office and they're breathing and I have a certain parts per million on the wall or in the return duct, that's fine. When they all walk into the conference room together, my return duct is going to still say the same thing, right? But I need to direct the ventilation air to the conference room, and I don't know that they're there because I'm not sensing in each room. So really, to do it correctly, every single zone has to have its own CO2 sensor. Basically, everywhere you decide to put a thermostat, you've defined that to be a zone. You need to put a CO2 sensor with the stat, right? That is the absolute best and most surefire way to do it. There is one controls manufacturer that does it differently. There is a portion in ASHRAE 62.1 called equation 6.1, and that allows you to do the multi-zone calculations, and you can pick critical zones like conference rooms and put your sensors there, and then use the calculations to kind of predict everything else that's going to happen. I've never done it that way because only one manufacturer of controls has the logic built in to do that, so I'm not sure how well it works or doesn't work. But all the other manufacturers all put one in each individual zone and makes it real easy, makes it real clean, makes it real safe and guaranteed that you got the right amount of air. So then what happens in each zone is if my particular zone needs more fresh air, my CO2 rate has gone up because everybody showed up to the conference room, if you will, I will first tell that particular zone to start opening up its damper. And then if that guy can't cut it and he opens up and he still can't bring the CO2 level down, then that damper will tell the ventilation damper outside to increase his fraction of outside air. I know what everybody's thinking. They're thinking, oh, you're bringing more air into the room and you're bringing more outside air and you're going to freeze people out in the winter. It's not true because I'm never going to go more than what the code air required. So a better way to think of it is I'm going to lock my damper down at the code required air, and then if everybody does not show up in the conference room, then I'll modulate it back. Think of it that way, and then you'll understand that you're not going to overcool the spaces. Additionally, we have algorithms built into the zone damper controls to make sure we don't accidentally overcool, and we can always use the reheat to temper it back up. Reheat that I would have been running anyway had I been bringing the ventilation rate in all the time. Cliff asks if the chart's based on office space. I don't remember what chart you were looking at, so this one right here, I'm assuming. If it is, Cliff, then yes, this one was based on an office building, and I think it was 6,000 square feet when I did the example. Marty asks, how often, in my experience, do CO2 sensors need calibration? How many years do they last? I used to have to calibrate them we tell everybody every year, but it was kind of like every 2 years was when they really kind of got done. But the new ones that we've had for the past 8-10 years, maybe even a little bit longer, the automatic calibration ones, like I said, we'd go check them, and typically they were within 50 parts per million, which is horseshoes and hand grenades close enough and within the specs of the original sensor, so we would leave them. And like I said, I've replaced 8 out of several thousand. Now there's probably another several thousand that I've never personally gone back and tested, so I don't know about those. But even if you say the 8 is 50 instead of 8, it's still a pretty low rate. So I would just say you check them every couple years. If it's an industrial application and you're manufacturing stuff that's off-gassing CO2, that's different. Use a different grade of sensor. You calibrate those differently. All right, I think we got everybody's questions for now. All right, so there are rebates in different states. I won't go through theirs. You can kind of see what they are for your individual state. Most of the states have something going on, and the ones that don't usually allow you to do it as a custom type thing. But these are ones for the Midwest, and there's other states out there as well that have rebates for CO2 specifically. Let's talk a little bit about ERVs. I'm not going to spend a huge amount of time on that because I want to spend the bulk of our time on staged air volume type stuff. But we'll talk a little bit about ERVs, and specifically talk about ERVs and how they most likely relate to rooftop units. So ERVs are a fantastic technology that saves a lot of energy. They've shown up on some of these Department of Energy top technology lists for quite some time. At the time this particular list was done in 2012, it was ranked second only to radiant cooling chill beams for potential energy savings at 0.55 quads for the country, whereas chill beams were 0.6. Everything else was rated lower than that. So they were saying ERVs have more potential to save energy for the country than variable volume refrigerant systems, than microchannel heat exchangers, than duct sealing, than cold weather heat pumps, than DOAS systems. They were saying it's basically one of the things you could do the most to save energy. So for those who don't know, ERV stands for Energy Recovery Ventilator. The big question we always ask is how much outside air are we talking about? If you don't have very much outside air, there's no point in me trying to do some kind of recovery to temper it up for you. So the more CFM you got, the more better. Basically what the ERV does is it preheats, pre-cools, prehumidifies, and dehumidifies your incoming ventilation air. So if I take a look at the example in the bottom left-hand side of the screen, it's a summer scenario down there, I have this flow of exhaust air that's, in this example, 75-degree dry bulb, 63 wet bulb, that I'm going to run through my exhaust fan and throw away. Then I decide, well, instead of doing that, what if I reclaim the energy from that air and use that, in this case, to pre-cool and pre-dehumidify the ventilation air. In my example on the screen here, I happen to be showing a wheel. It spins through the two air streams and grabs the energy from this return exhaust air and transfers it over to the ventilation air coming in from outside. In this example, it's 95, 78 degree day outside, which is basically the nastiest day we can get here in the Midwest, and it brings that up to 81, 68. So on a 95 degree day, my rooftop is going to see 81 degree incoming air. And I'm going to dehumidify it from 78 wet bulb down to 68 wet bulb. By the way, evaporator coils on rooftops are rated for 80-67. So if I can get the ventilation air close to 80-67, then it's basically like I don't have any ventilation air that has to be treated. So that's usually one of my targets when I'm sizing an ERV, is to get things to 80-67, and I know the rooftop or the air handler or the fan coil or whatever will be able to handle it from there without any problem. And that's nice, and I get some free cooling benefit here in the summer and definitely some dehumidification benefit, which is really nice. The winter on the right-hand side is really where it pays off. In this case, I'm throwing 72-degree air away. Instead of doing that, I transfer the energy to the ventilation air. This is a 7-degree day example outside. On a 7-degree day, I turn that 7-degree air into 53-degree air before it even enters the gas heat exchanger of my rooftop unit. So on a 7-degree day, my rooftop thinks it's 53 outside. Sometimes I don't even have to kick the heat on because 53 might be enough to avoid the heat having kicked on for a while. Additionally, I get some free humidification benefit. It was 9-degree wet bulb outside air I was sucking in. Because I recovered some of the moisture of the exhaust air, I've tempered that back up to 40-degree wet bulb. So I've preheated it and pre-dehumidified it. So it is quite beneficial in those regards. You can adapt this to existing systems, although it's usually better if you've correctly sized the rooftop to complement the ERV. So we'll talk about that here in a second. Why is my slide not advancing? That's sort of annoying. Okay, there we go. Typically, we use ERVs in this market, which are the enthalpy recovery ventilator type. There's also HRV, heat recovery ventilator. HRVs don't do the latent energy. So HRVs just do dry bulb temperature improvement, heat or cool. ERVs do dry bulb, heat or cool, and they do the wet bulb side, the latent energy, humidify, dehumidify. Right? So you're getting 4 things instead of 2 things out of it. So we almost exclusively use ERVs commercially in this climate zone. The only time we don't use an ERV and we recommend an HRV is when the indoor humidity is expected to be regularly worse than the outdoor humidity, right? So that basically means locker rooms that have showers, a greenhouse where they're spraying water on plants, something like that where moisture is being introduced, some kind of giant lobby that has some kind of water fixture, fountain type thing, something like that, then we might not want to recover the moisture in those cases. But for all your offices and classrooms and stuff like that, we definitely want to do it. Sometimes it is required by code, and we will talk about that a little bit today. Paybacks are usually pretty quick, generally speaking under 2-year payback. This is a chart that a lot of our sales guys use with rooftop units. This particular chart was based on 95-degree outside, minus 10 in the heating side, so it's pretty extreme days it was based on, but it kind of covers everything in our area if you do it that way. And it was based on someone upgrading their rooftop and buying a new, smaller rooftop with an ERV bolted to it or inside it or something like that. So basically, if we take a look at outside air, if I take 1,500 CFM of ventilation air coming in, I'm able to downsize the rooftop by 4 tons. That means if you were going to buy a 15-ton rooftop, now you're going to buy an 11-ton. Right? If you can't buy an 11, you'll buy a 12.5 or whatever the size is. Right? But you can buy one that's literally 4 tons smaller than you thought you needed. Now you still got to be able to make sure you can do the CFM and static needed for your duct system, but I can get a much smaller refrigeration size of my unit. On the heating side, I was able to drop the heat exchanger size by 120,000 BTUs, so that'll typically take you out of the quote-unquote medium heat unit and down into a low heat unit. On that 95 degree 75 wet bulb, 74 wet bulb day, I'm able to get down to 8067, which is my typical goal. And then on that minus 10 degree day, I was able to heat it up to 50 degrees incoming air, just by spinning a wheel in this case. Payback was really good, 1.6 years, 63% return on investment, life is good. I can take a much more extreme example, 12,000 CFM of outside air, which is huge. I got a 31-ton reduction in the size of the rooftop that I need. So if I used to need, whatever, a 70-ton unit, now I'm going to buy a 40-ton unit. Almost a million BTU smaller on the heat exchanger, 0.1 year payback, literally a 1 month payback basically, right? Now in defense of this number, the reason why it's such a good payback is most of you guys know with rooftop units, like I said on week 1, if you can get down, below 30 tons, down to that 25, 28 ton rooftop chassis, you are more in line with a quote-unquote commodity rooftop unit as opposed to a semi-custom rooftop, so the cost goes down dramatically. So that's what happened in this case. We're able to get into a much smaller chassis unit where the cost was much lower for the unit itself, which made it easier to pay back the ERV because the rooftop cost savings when we bought the new rooftop. Good applications are kind of similar to DCV anywhere with lots of people. So schools, offices, theaters, gymnasiums, nursing homes, stuff like that are good candidates. Hospitals are good candidates and much better than DCV because I don't have to worry about modulating the air back. There are different types of heat exchangers, and I'll briefly cover them. There's a plate style. These can be made of metal, which is an HRV only, or they can be made of some sort of fibrous material, which allows for latent transfer. It's basically a wicking function. So it basically pulls the moisture through without pulling the actual air molecule through. If you want, you can take 2 glasses of water and set them on your desk, put food coloring in one and not in the other, and then put a piece of string between the two. Eventually the vapor pressure will wick the moisture up the string and into the other glass. And instead of 1 dark blue glass and 1 clear one, you'll have 2 light blue ones. Same basic principle applies here. We wick the moisture through to pre-humidify or dehumidify the air depending on the season. Wheels are by far the most common type because they have the largest recovery possibility, and they are typically less footprint required. The wheel spins between the 2 airstreams and transfers energy that way. You can get a sensible only one, or you can get one that is sensible plus latent. That one typically has a desiccant impregnated onto the plastic that can absorb and release moisture. So when you get those little packets in your electronics or your shoes or whatever that says do not eat desiccant gel, that's what's on there, right? Those are in your electronics box to keep the moisture neutral in the box so you don't damage the electronics when they ship it to you. Same exact thing happens here. This really helps illustrate why we use wheel types instead of plates for many applications. We can simply just recover much more BTUs. It doesn't mean we don't use fixed plates. We use a lot of them here, but the ERV wheel is the most common choice we make because of the recovery possibility. Let's see if any questions for right now. Let's see. Boris asks, why not directly recirculating or mixing the return air? I'm not sure what that one was in regard to. One of these ones, I'm assuming. I'm not sure what that was. We'll have to talk about that offline. I'm not sure the question there. Doesn't the wheel need to be dried? I'm not sure what you're referring to there, Dan, but I'm thinking you must be thinking of a not a heat recovery application, but perhaps a wheel reheat application where you need to use gas-fired heater to re-energize the desiccant material. That's not really an issue on this type of recovery, and we're going to go through that a little bit here. Gil asks on that 12,000 CFM example if that was a wheel integrated unit or outside the unit. It was outside. It was a packaged rooftop unit bolted to an ERV, and I'll show you some pictures of that in a little bit. But that really is what is the most cost-effective scenario. Syed asks if ERVs are approved for the city of Chicago due to cross-contamination possibilities. ERVs are approved, and I believe I have some slides on that, and I will show you those in a couple minutes. Let's kind of get along to that. So there's a couple different ways you can tie ERV into a rooftop. There are ERVs that are quote-unquote bolt-on. They literally hang off the side of the rooftop where the economizer and power exhaust would hang, right? And they typically have a little economizer damper in there as well, and an exhaust cycle with a bypass damper. So you got an economizer, power exhaust, and ERV all in one box. These can be retrofitted onto existing units, although you do kind of lose the benefit of the downsizing that I was talking about before. But it can be done, and it is typically cost effective. It's going out my mouse again. Okay, there we go. This is more like that 12,000 CFM example, Gil. This is a much smaller unit in this example. But on the left, you have a packaged rooftop unit. On the right, you have an ERV. And then they're both sitting on a common curb. We call it a combo curb. It has duct transitions inside it. And it allows us to route the return air through the ERV and out, and then bring the outside air through the curb and into the rooftops return section. So this is an extremely cost-effective way to do it. Yeah, it's a little bit ugly, I agree, but it's on a roof, and no one sees the curb on a roof unless they're on the roof, so it's not like you can see it from the street line, so it's not a big deal. But it does allow us to use packaged, standard, off-the-shelf rooftops with the ERVs and kind of get the best of both worlds in terms of first cost and energy savings. We can definitely improve the humidity in spaces with an ERV by pre-humidifying and pre-dehumidifying the outside air. As you probably already know, lots of bad things happen when you get to too dry or too moist conditions, and commercial buildings for the most part have neglected this issue for quite some time, and an ERV is going to help us with that. I'll just show you one example of what happens in a lot of buildings. So this middle column here is showing you a building that's designed for 100% occupancy, and in this example it's a 95-degree, 76 wet bulb day, so like the nastiest day you can think of, in a climate slightly worse than ours, like St. Louis-ish. And in this case, they got 15,000 CFM of outside air. They're getting a 53-degree dew point off of the coil, which allows them to maintain 75 degrees in the space, 48% relative humidity. Life is good. Everyone is happy, right? If you look at that previous chart, by standard 60%, I'm usually good. ASHRAE standard 55 and ASHRAE standard 62 both want you to stay below 60% in the space also. However, on a regular 1 or 2 stage package unit, what ends up happening is really the right-hand column. Well, it's probably not fully occupied. It's probably partially occupied, or it's not really 95 outside like rooftops are designed for. It's really like a more typical day in Chicago, 80 degrees outside, which means I'm cycling my compressor on and off, or my compressors, if I have 2 of them, on and off. That means my evaporator is not wet for as long of a duration of time, which means I'm not dehumidifying as much. The end result is, assuming I don't modulate the fan speed, which we typically don't, I got 15,000 CFM still, but I get an average dew point off the coil of 65. Yeah, sure, I get like 48, and then I get 72, then 48 and 72, but on average it's like 65. What ends up happening is I still get my 75 degrees in the space because the thermostat's the one thing in the entire building that's always happy no matter what, but I end up with a much higher relative humidity, in this case 71%. If I have 70% humidity for about 2 weeks, I can grow mold. If I have 80% for like 3 days, I'll start growing mold. So I really do want to try to keep it below that, and having better staging on my equipment, changing the airflow like we're going to talk about in a couple minutes here, or adding in an ERV are all ways we can kind of really improve upon that. Last slide chart for the whole class, I promise. The blue blob, if you will, is showing you the range of what a normal rooftop unit has to handle on an everyday project. I got to handle all the way down to 0 degrees or whatever. I got to handle up to 95 degrees or whatever it is there. Some really dry day, some really moist day. I got to handle everything in that red blob. Well, if I'm able to preheat, pre-cool, pre-dehumidify, and pre-humidify my air, I don't care about the red blob anymore. Now I'm sizing my rooftop for the blue blob. Blob's a technical term for those that don't know. So I'm going for the blue circle there. In terms of my rooftop sizing, I'm much more appropriately sized to be able to handle that blue scenario because I don't have to deal with the big range. The ERV is trimming everything for me. It's humidifying, dehumidifying, heating, and cooling, so I don't have as much to deal with the rooftop, which means the rooftop doesn't have to be oversized, it doesn't have to short cycle, all that great kind of stuff. Oops, let's keep on trucking. ERVs are sometimes required by code. If you are on the 2006 or 2009 IECC code, if you have a system that has 5,000 CFM of supply fan with 70% outside air or more, you are required by law to put an ERV in. That does not include a lot of buildings because 70% outside air is not extremely common. However, the new code follows our map that we talked about earlier. And if you are with me today in Chicago, you are on climate zone 5A, folks in Wisconsin 6A, Minnesota 6 or 7. If you're in Miami, you're down in 1, etc., etc. Got the same map we talked about last week, right? So if I look at 5A where I'm at in Chicago, for climate zone 5A, if I have 70% outside air in the new code, the 2012 code and later, which is code in Illinois and very soon Minnesota as well, then if I have 1,000 CFM of 70% outside air, I got to do it. And I also have tiers for 60, 50, 40, and 30% outside air. If I got a system that's 5,500 CFM of supply air, right? What's 5,500? Nominally speaking, 13-ton system, right? 13-ton system and larger with 30% outside air, I have to put an ERV on by code. 30% air happens a lot more than 70% air. Yeah, it won't be every space, but it'll start including things like schools, daycares, and those types of facilities. All right. This data I showed you before and data like that, we calculate with a particular software program that one of the wheel manufacturers puts out, Air Exchange, and they custom brand it for all the different cabinet manufacturers and all that. A report looks something like this. You put in the conditions you want to base it on and all that kind of stuff. It tells you what conditions you're going to get off of the wheel, both in the summer and the winter. In this case, 80-67 and 52-42 in the winter. It tells me down at the bottom over there how much I can reduce my heating and cooling size by, right? So I can reduce it by 3.8 tons, 3.8 tons and 120,000 BTUs, right? That same tool then can aggregate everything for all the ERVs that are proposed on the project, and you can go down this middle column here and see how much cooling dollars I'm going to save. And by the way, at the time this was generated, it was based on 10 cents a kW and $1 a therm. Our electric is still around there, and our therm cost is down a little bit, but you get the idea. This is how much cooling I'm going to save, $3,400. My heating savings is $32,000 because this is Chicago area and it's a big savings. I'm also going to spend an extra $4,600 in extra fan energy because it's not free to push air through a heat exchanger, in this case a wheel. I got to pay to push that air through there, either by speeding up the fan of the air handler or in the case of this project, by adding small fans to the ERV to do that. So I can save save $3,500 in electric on the cooling, but I pay $4,600 in electric on the fan. So typically you won't see electric utilities rebate ERVs. You will, however, see gas utilities rebate the ERVs. But electric guys will do it on an all heating project with electric, but they won't do it on a gas project. This is a pretty big savings. Overall, net, it's a $31,000 savings for this project with 11 ERVs. They ended up doing 9 of these on the project. They didn't do number 7, they didn't do number 5 because the savings just wasn't big enough to justify it for them. But these kind of tools are very helpful, and with all those kind of tools, we can put it into different spreadsheets and show you what the the net present value is, and the internal rate of return, and the payback, and all that stuff. Because sometimes the bean counters you're talking to need that data. So for all kinds of energy stuff, I do charts like this to show the payback in the language that the bean counter guy needs to see it. Because I'm a mechanical guy and I'm not a good bean counter, so if I have the little spreadsheet set up, it's easy for me to plug the numbers in there. Like I said, there are rebates for ERVs. Typically, they're mostly on the gas provider. So you don't see one here for ComEd, but Peoples and North Shore Gas do have a rebate. There's rebates in Wisconsin, Minnesota, and then most other utilities do it as a custom. If you want to do an all-electric building with an ERV rebate for ComEd, you can do that. It's just got to go custom. All right, let's see where we are in terms of poll questions. Let's pop one of those guys up. All right. True or false, demand control ventilation is required by code for densely occupied spaces in at least 35 states. While you guys are answering that, I am going to look and see if you typed any questions in for me. Oh, I forgot to answer Syed's question about Chicago code. All right, so there's 2 things that come up in the Chicago code, Syed. So one is that in order for an ERV to be approved in the Chicago code, it has to have 0 cross-contamination. So AHRI rates ERV wheels and ERV cores and stuff like that, and they have this term called EATR, exhaust air transfer ratio. That's how much of the exhaust air accidentally leaks back into the incoming ventilation air. Normally it's general exhaust from the building, so it doesn't really matter, but if you're doing toilets or something like that, then it could be a problem. But that EATR is a tested and published number. The City of Chicago requires 0. So if you have AHRI certified data saying that you have 0 EATR, you can use it in the city of Chicago. By the way, the city wants 0.0. 0.1 doesn't count for the city. I've learned that the hard way. It's got to be 0.0. I've done it with wheels, and I can certainly do it with fixed cores. Fixed cores are always 0. They're guaranteed, right? But a wheel you can do by putting the fans in a certain position. And I got a whole separate webinar of 2 hours on Ervs that I could send you guys a link to if you want to see how to do that specifically. The second part of the City of Chicago code is that it says if you're using certain classes of air, specifically for this example, toilet exhaust air, then I can't have the wheel and successive cycles of the airflow. Basically, they're saying you can't have the core, the heat exchanger, in motion between the two air streams for certain classes of air. So if I want to do an ERV on general exhaust air, I can do it with a wheel. If I want to do it on toilet exhaust or something more caustic than that, then I am prohibited from using a wheel, and I have to do it with a fixed plate core. If you want to talk more about the City of Chicago, let me know. Let's go back to our poll question and get that wrapped up. And I'll go back to some of your guys' other questions as well. So most of you guys got it correct. 96% of you said it is true. At least 65 states require DCV in a densely occupied space. They do define densely as different. Some of them say 40 per 1,000 square feet. Some say 25 per 1,000 square feet. But those are both in there. All right. Let's talk about staged air volume. I'm going to shelve some of your guys' questions for a little bit because I want to make sure we get staged air volume covered, and then I'll answer the questions at the very end just because I want to make sure we get everybody that wants to hear the staged air volume stuff wrapped in here. All right, so, oops, sorry, okay, there we go. So staged air volume, SAV, this guy does go by several different names. You will hear it called by some manufacturers as single zone VAV. That's an old name that we used. We were using it 18 years ago when I started here. We weren't doing it on rooftops, we were doing it on air handlers. We called it single zone VAV. One manufacturer calls it multi-stage air volume. Carrier used to call it adaptive fan control until a couple years ago when they decided to use the SAV name like some of the other guys, because SAV sounds kind of like VAV, so people sort of kind of get it a little bit, although it does kind of confuse things sometimes. But you might hear any one of these names. For today's purposes, I'm just going to call it SAV. So really the idea is this kind of squeezes in between your traditional constant volume rooftop unit and your full-on VAV unit. A VAV unit is designed to be used with zone dampers. You put a pressure sensor in the duct system. As the zone dampers throttle back, the pressure in the duct system builds up. The pressure sensor recognizes that, and we slow the VFD down. Nowadays, we used to do it with guide vanes and other stuff, but we slow the VFD down nowadays to provide energy savings and to reduce the static pressure in the system. Staged air volume is a little bit different. There are no pressure sensors involved in this discussion because there's no zone dampers involved in this discussion. So the pressure in the duct system doesn't really change on its own, right? So when do we decide to slow the fan down? We slow the fan down depending on how many stages of heating and cooling are running. Now that may sound a little bit weird, but quite honestly, residentially, we've been doing this on standard mid and high tier equipment for 15, 20 years, right? A variable speed furnace has been doing this forever, literally 15 plus years, right? So if I have 1 or 2 stages of cooling running, I'll run at 2 different unrelated speeds. And then heating will have its own speed, and vent-only mode has its own speed, and those kind of things. Now right now on most rooftop units, we are limited to only 2 speeds. It's not because the rooftop can't handle it. It's not because the fan can't handle it. It's not because the VFD can't handle it. Interestingly, it's because the economizer can't handle it. And I will explain that in about 5 minutes. So right now, I'll just take my word for it. So the way we're doing it right now is that if you have heating on, you get full airflow. If you have 2 stages of cooling on a 2-stage system, you get full airflow. If you only have 1 stage of cooling, we cut your airflow down to about 67%. The number changes a little bit depending on the unit specifically, but for argument's sake, about 67% for 1 stage of cooling. And if you're in vent-only mode, we do the same thing. We go down to 67%. Now, I'd prefer to do it the way that DOE study said and do it like 40% in the vent mode and things like that. But right now, I only have 2 speeds to work with, and I'll explain that. Right? So why do we do it on the cooling side instead of the heating side? There's a few reasons for that, and we'll talk about that. The big question always comes up is why using a VFD? Why don't you just use a 2-stage motor? Most of you guys at this point are probably aware VFD costs have dropped dramatically in the past 20 years. A lot. I mean, you can literally get a VFD for a 3 horsepower motor for like $500. It's really low. So a VFD is literally cheaper than a 2-stage motor. I can get a VFD and a standard speed motor cheaper than a two-stage motor. So that's the main reason. Plus, it provides some other nice benefits like the soft start capabilities and lower demand charges when the units first kick on and those sorts of things. The quick spiel on VFDs, I'm sure most of you guys know. You've probably seen me talk about it before. But in the United States, fan systems, on average, are oversized by 60%. That's not me saying that. I probably think the number's higher, but that's Johns Hopkins University study saying that. So on average, things are oversized by 60%. So I like to ask building owners, if you have a motor running at full speed, like all of them are, and it costs you $1,000 a month to run this motor, if I cut it down to 75%, how much will it cost you? And they say it'll be $750. I say, okay, would you like to save that $250 a month? And they say, yeah, it's a great idea. I said, well, guess what? It's actually going to only cost you $420, not $750. And then I say, well, if you cut it in half, how much would it take? And of course, they're thinking $500, but they don't say that because they know it's a trick question at this point. It's about $125, right? And that's due to the affinity laws or the fan laws. We call them the affinity laws so the pump guys don't get mad, right? But the fan laws, affinity laws are really what's driving that factor. And the way that basically works, in quick summary, and this is true for any VFD, the brake horsepower varies with the cube of the speed, right? So that's that formula up on top there. Brake horsepower 1 over brake horsepower 2 equals the cube of RPM 1 over RPM 2, right? So what that means is I don't have a straight linear line that I'm working with, right? So as my CFM reduces, like it is in that orange line there on the drawing, I'll try to highlight it here. That orange line on the drawing, as my CFM reduces, my brake horsepower comes down exponentially, if you will, right? So it's a big dramatic drop. If I can just get you to lower your speed 5, 10, 15, 20%, it's going to be a huge payback, a really huge payback. So like it says down here, if I cut your speed by 33%, I save 69% of the energy savings. It's dramatic because of that cubed function, right? Most of you guys are familiar with that, so I won't beat that to death. Just know that that's the third affinity law. Or if you're a fan guy, it's the third fan law. If you're a pump guy, it's the third pump law. So like I said, we run reduced airflow when we go into vent-only mode or one-stage cooling mode. Now, someday we'll want to do this on the heating side as well, but we have to do some things to make that happen with the economizer guys. There's also some concerns about cutting airflow back on heat exchangers for gas-fired heat because we're already providing too little airflow in many cases with too high of discharge air, but that's a whole other discussion for another time. The good news, as we talked about last week, vent mode is like 60% of the hours. We already kind of established that. So if I'm cutting your airflow back for vent mode, that's really where the big savings is at. The fact that I get to cut it back for first stage of cooling also is kind of a bonus, and really it's a dehumidification bonus. If I can slow down the airflow going across the evaporator coil, it's also going to take me longer to satisfy the thermostat set point, which means I'm going to get a longer run cycle. And the slower I move the airflow through there, the more I can change the sensible heat ratio, and I can do better dehumidification that way as well. So having the staging capability combined with the fan staging capability is really a great dehumidification benefit on a rooftop unit. Another reason why we're doing it on the cooling side instead of the heating side, because we only have one we can do it on right now with the economizer guys, is because ASHRAE 90.1 2010 and 2013 both require you to do this by code. So if you are in an area that's following 90.1 as the code, then you have to do this anyway on anything that's 110,000 BTUs or more, right? So that is, what is that, 9-ton system? Yep, 9-ton system. I gotta do it. It's not a choice, right? Now, a lot of areas don't follow 90.1 as their code. They follow IECC. IECC did not put this into their code, so you don't have to do it in a lot of spaces, right? But if you are on 90.1, you have to do it. Some cities have adopted 91.1 in some states, and more interestingly, if you're doing a LEED project, 90.1 is a prerequisite for compliance with LEED. So if you want to even have a chance at getting LEED status, you have to do everything in 90.1, which means you definitely have to do staged air volume on any units, and this is rooftops or air handlers, any units that are 9 tons and larger or larger than 9 tons. You got to have the ability to step down the airflow when only one stage of cooling is running. So it's required. This is the same chart I showed you last week. The difference is here, I've added in a couple more examples to kind of explain a little bit better. So once again, forget the blue stuff right now. That's SEER, that's for the little units, and forget the EER because nobody cares about those because that's full load, right? So I'm really looking at the green one, which is the part load efficiency without staged air volume and the part load efficiency with staged air volume. The fans, if you didn't know, for rooftops and fan coils and stuff like that, the fan energy is part of the total rated energy of the product, right? So the EER and the IER include the fan energy. So I can go, in this case, on the code minimum unit, I can go from 11 IER to 12.5 by putting a staged air fan on. Right, on the mid-tier one, I can go from 13 to 13.5, right? And then on the high-tier one, it's already built in, and I'm already up at 19 IER. But the other thing to note that's interesting is that sometimes it might make more sense, instead of taking my money and spending it to go from the code minimum unit to the mid-tier, mid-efficiency refrigeration system unit, I may want to take my money and go from code minimum without SAV to code minimum with SAV. Right, make this leap from this green to this red one over here instead of going up to the next cabinet of unit. Right, if you want to do both, that's even better. Right, you'll get even better efficiency. And if you want to go all the way to the max, that's the best. But sometimes, depending on the exact scenario of the rooftop, it makes more sense to put the variable fan on there than it does to upgrade to the next tier of unit. Here's some examples that are showing. Actually, we'll just skip this. This is a Tennessee example. It's meant to be kind of all-inclusive for the whole country, but everybody on this webinar, for the most part, is well north of Tennessee, so I'm just going to skip it. The takeaway here is that you can do lots of different stuff with different size units, and depending on where you're at in the world, this is showing you 10, 15, 20 tons. Sometimes it makes more sense to go to the entry level with SAV than it does to go to the mid-tier unit. All right, it depends on the size and the climate and all that stuff too. But we'll switch over and look at an Illinois example. And by the way, I can do examples for anywhere you want, and I have a bunch of them that I already do for Milwaukee and Madison and Duluth and South Bend and everything else. I can send those to you real quick. But here's a Chicago one, because most guys on this webinar are from Chicago. This is a software tool that we use quite a bit, and if you're interested in learning more about this software tool, we use it in the class this Wednesday. It's an all-day class on rooftop replacement, and we talk about a lot of the same stuff we're talking about in this webinar, but in greater detail, and we integrate it with the software discussion and install it on your computer and show you how to use it and all that great stuff. This particular software is a carrier software, but I'm just using it for generic purposes today. Basically, I got a 10-ton load in this building. I'm using the EIA data for electric rates, which is 8.5 cents and 81 cents a therm in this example. But you can punch in anything you want. You don't have to use the EIA data. So you got your baseline case in the left-hand column, right? That's this column right here. And then you got your proposed case. In this particular case, I chose the exact same model number of rooftop unit, with the exact same size heat, the exact same size cooling, the exact same EER, both 2 stages of cooling, exact same size on the heat, both 82% on the heat. Everything's identical. The motor horsepower is 3.7 brake horsepower. Literally, the only thing I changed is 1-speed versus 2-speed motor, right? The staged air volume. Left everything else absolutely identical, right? So we can see what that savings potential is going to be just by doing that one thing on the exact same unit in this case, right? So this is basically the payback off of that. Over 5 years, it's going to save $2,800, right? Annually, that's $577, which is 30% of the operating cost of this unit, right? It's pretty impressive. You can see where the savings comes from. This is just one screenshot of the multi-page report, but I don't want to do everything in one. We'd be here all day just talking about this. Like I said, it's a whole separate class. But the fan savings is $627. That's pretty good. There is a slight cooling savings that's involved in here, and there's a slight penalty on the gas heating side because I don't have as much waste heat off of the fan motor because I'm running it at a reduced capacity. So somewhere in the course of the year, I'm making that up a little bit. But I'll happily spend $62 more on gas to save $500 or $600 some dollars of electric, right? So 30% savings for Chicago example, and most of the Midwest ones are fairly similar to that example. You're not limited to doing this on 2-stage equipment. You can do it on 3-stage equipment or even more, but it does require you to have an economizer controller that's more robust than the standard one, and I'll talk about that in a second. But if you are able to do a 3-stage unit, it's kind of nice in that regard because you kind of get most of your bulk hours on that second stage of runtime. And very few times you actually need the 3rd stage. So it's really kind of like you got a 2-stage unit, plus you have that 3rd stage for when it really is a hot day, which hardly ever happens, but when it does, you're ready for it. So you get better comfort control, better temperature control, better latent control, and better fan savings out of the whole deal. Doing this is not as hard as you might think. I'll show you a DDC control example, then I'll show you a non-DDC example. So you got to have an inverter duty rated motor. If you want to retrofit it on a regular motor, chances are you could probably do it. Talk to your VFD guy, talk to your motor guy. I don't know how many times I can tell you we've retrofitted VFDs on standard motors and everything's been fine, but you do have to have the conversation with the building owner and say, yeah, we should change the motor out. If they don't want to do it, then it's on them, and then if the motor fails prematurely, at least you've given them the choice. But usually you can put the VFD on the motor, and lots of them are inverter rated now on the newer units. I need something to tell the control system to give the VFD the different speed signals. So we typically do that with this fan relay board. That's part of the discussion. And we have our sensor reporting back to our backnet controller, which we call RTU open. The central terminal board is already standard on the unit. So really what we're adding is the VFD and the fan relay board to the discussion. The DDC control system, is already taking control of the economizer directly. So when I have DDC controls, I have much more flexibility, and I can do more than those 2 stages in some cases, because the DDC controller might be able to handle more than 2 stages of fan positioning for the economizer. If I go electromechanical, meaning non-DDC, and I use a standard thermostat, then I'm going to be stuck using a regular Honeywell economizer. I'm going to kick this computer if it doesn't start clicking. A regular Honeywell economizer. If you didn't already know, all the Honeywell economizer model numbers are being obsoleted, and the only one that will remain is the Jade economizer controller, which is the one on the screen here, the W7220, that replaces all the other models. And one of the reasons for the existence of this product, other than it's easier to wire and configure and all that, is that it has the ability to have more than one minimum ventilation set point. So I can literally have one for first stage of cooling and one for second stage of cooling, which I'm going to need when I want to do this staged air volume. So that's typically how we're doing it on these types of units. That controller came out about 3 years ago, and it's going to become your de facto standard on all rooftop units that use Honeywell economizer controls, which is like 98% of the market. Here's the reason why you need to do this with a 2-stage economizer position. All right, so here's my normal scenario. My fan's running at 100% capacity. I got 100% supply air, 100% return air. Everything is basically normal, except for I can't click my mouse. Come on, man. That's not fortunate. Okay, there we go. Not cooperating with the mouse today. All right, so instead of bringing 100% return air, I might have 80% return air, 20% makeup air from outdoors, right? So that's 800 CFM in this particular example. Everything's fine, everything's great. Now when I slow the blower down to 67%, I've reduced the supply air and I've reduced the return air. So I've inadvertently also reduced the outside air. Right? If the blower is moving less air, it's sucking less from the return hole and it's sucking less from the outside air hole, assuming I don't move the dampers. Right? So I'm only bringing 520 in. So I got to do something to open up that outside air damper more to continue to get my code-required 800 CFM of air. Right? The way to do that is having an economizer that has 2 minimum positions. In this case, it has one for stage 1 and it has one for stage 2 of cooling. And both of them will get me 800 CFM, but at a different damper position because the fan speed is different. Right? So that's really why we're doing that. Once Honeywell or someone else comes out with another economizer controller that has 3 or 4 steps instead of 2 minimums that are possible, then we can start doing more on the staged air fan speed side. Right now we're limited to 2 fan speeds because we only have 2 economizer speeds, unless you want to go the DDC route, which is totally fine. Then you can do whatever you want. There are rebates for doing this. It can be a little bit tricky. In some places, it's specifically called out, like last June, ComEd's new ARC, Advanced Rooftop Control Rebate, specifically calls this out, staging the fan like this, and you can do it as part of that rebate. But in most places, you can even do it as part of the regular rebates. There's certainly rebates for VFDs, and they don't prohibit you from doing it on staged air volume. They just say you have to have a means for changing the fan speed based on what's going on in the building, and this is definitely a way to do that. One place, specifically Wisconsin, as of this January, does not allow you to do it on SAV. They want you to do SAV under the custom program instead of doing it under the regular VFD program. But everywhere else has not had a problem with it. Minnesota, ComEd, NIPSCO, so far have all been cool with us submitting SAV applications as regular VFD applications. It's not a lot of money because it's like 2, 3, 4, 5 horsepower, right? So you're getting a couple $100, but it kind of helps pay for it a little bit. I don't have time today to go through individual products from individual manufacturers. Plus, obviously, I only like Carrier and Bryant. No, I'm just kidding. No, actually, I'm not kidding. But there are manufacturers that have this as a standard option you can buy on new rooftops. When I made this presentation last year, there were 4 of them that were doing it. There could be more now. I apologize if there is. But there was a lot of people that can do it. So the point there is you can specify this and get multiple bidders for staged air volume. If you want to do it as a retrofit, you can certainly do that as well. There are 3 manufacturers, like we said earlier, that make retrofit kits to do this, and that's one way to do it. However, the other thing I've been doing lately is I've been using standard off-the-shelf Honeywell parts to do this. To the point now where we got the Honeywell guys looking at making it into a kit of their own. So it's pretty easy to do that. If you want help using Honeywell controls to retrofit it on an existing rooftop, you can do that. Now, if your rooftop's 15 years old, it doesn't make any sense. Buy a new rooftop. But if your rooftop's 5 years old and it's a decent size, 15, 20 tons or whatever, then maybe it makes some sense to retrofit it. You got life left in the unit. I get it. Whether you're going to do it as a new rooftop with factory installed, which is really easy to do, you just basically hook up a regular thermostat. The only thing you have to do different in the field is you have to configure 2 minimum set points on the economizer. That's it. Other than that, it's super easy to set up. If you're going to do DDC controls or some version of one of these packaged guys kits, Catalyst, Enerfit, and Digi RTU, you got to determine whether they're using DDC controls to make it all happen and whether you need to have special training and knowledge to use those controls or not. They all do it a little bit differently. If you want to talk about any of those brands, let me know. I worked with some of them before. Sometimes also, if you do staged air volume with certain manufacturers' equipment, it prohibits you from using other accessories because they don't have the control ability to handle that. So sometimes they won't let you do staged air volume plus an ERV or staged air volume plus a dehumidification system like hot gas reheat. Sometimes you can only do one or the other. So you guys got to pay attention to that too when you're designing your system out. And then, is the VFD factory programmed or is it field programmed? You want to make it simple, stupid. You want to make it factory programmed so you don't have to mess with it, and most of the manufacturers can do that. So literally you buy a staged air volume, for example, a Carrier one, because that's the one I know the best. All you literally have to do different than a regular rooftop job, other than order it differently, right, is you have to go up on the rooftop when you set the economizer position, you set it twice with the balancer. Once for low speed and once for high speed on the fan. That's it. Everything else is the same. Nobody even knows there's a VFD going on in the background. It's already factory configured. It's already set for the speed you need. Everything's done. If you want to use off-the-shelf Honeywell solutions, it ends up costing, in terms of parts, about $1,900 in parts for a 10-ton unit, and the price doesn't really change that much if you go up or down because all the parts end up being absolutely identical except for that second to last one, which is the VFD. I put a 3 horsepower VFD on this example, but you could have a slightly bigger or slightly smaller one. So the price could go from $1,500 to $2,500 or something like that, right? But basically, it's $2,000 of parts to do it. That just gives you kind of a check figure in your head. You also have the labor of somebody wiring all this stuff up, right? They're probably going to spend a man-day doing that. So it's probably really $3,000 worth of cost. And that is in line. It's actually slightly cheaper than some of these packaged retrofit kits. All right, the best time to do it's on a new unit, but you can do it as a retrofit, like we said. There's the wiring diagram that goes with it. If you want to do it with Honeywell off-the-shelf stuff, let me know. I'll help you out with that. All right, in our last few minutes here, actually let's launch another poll question so we get that knocked out of the way. Got a couple more of those to go. Then we'll do capacity control and I'll answer any questions. All right, so next poll question. True or false? You cannot put a VFD on a constant volume rooftop unit. Let's see, maybe I can knock out one of the audience questions while we're waiting for that. Jonathan asked earlier, does a rooftop integrated with ERV have a separate exhaust airstream for restroom or other required exhaust air, or does it remove a percentage of the return air? You could do it either way, Jonathan, but for the most part, it's removing a percentage of the return air is the typical means for that happening. Boris says it seems that this system is for 100% OA buildings, and that was regarding to the ERV question. That is not the case. We do ERVs on a lot of buildings that don't require 100% outside air. At 100% outside air, it's code required to have to do an ERV. But we do a lot of ERVs on jobs that are 35, 40, 50, 60% outside air because the payback's there to do it. And you can have the separate transitions in the ducting system for that to happen. So if you need help with that, let me know. I can help you guys with that. Ryan asked a great question. What kind of maintenance needs to be performed on a wheel? and how frequent they recommend maintenance. Most of the wheel manufacturers recommend annual maintenance. Usually I recommend an annual inspection, and if that inspection yields to needing the wheel to be cleaned, great. If not, maybe you can go every other year and clean the wheel. Wheel cleaning is very easy to do, especially if you have a plastic type polymer wheel with impregnated silica gel on it. Most of them, the big ones, are in pie shapes. You can take the pie shapes out and clean them that way. You can put them in a commercial dishwasher if you happen to have one there. If not, you can wash it with water and or non-acidic coil cleaner or dish soap if you want. That's fine too. If you're lucky enough to have a hose bib on the roof, great, you can do that. If not, you got to take them down off the roof and wash them and bring them back up. But typically, they say every year, and in practice, maybe every other year for a lot of applications. If you got something going on like tobacco smoke, which is really rare nowadays, then it's a much more frequent. It's every couple months. But for most places, you don't have that anymore. All right, we'll get back to some of those other questions after this here. So you guys got it correct. You said the answer was false. And obviously, you can put a VFD on a constant volume rooftop. We just talked about how to do that specifically. All right, we're going to have one more. We got one more poll question I'm going to do right now. Let's get that knocked out of the way. All right. True or false? Multi-speed fans are required by energy code. I guess I didn't really make that a fair question because I didn't say energy code in what state. All right, well, I guess either way you answer it, you're going to be right then. It's just going to be a freebie question because either way you're going to be right depending on which state you were thinking of in your head or what standard. All right, so the correct answer on that should have been false. Stage air volume multi-speed fans are not required by energy code in any of the states that any of you guys have logged in from. So Illinois, Wisconsin, Minnesota, Indiana, Iowa, Michigan. I see people from all these states on here. It's not required in any of your states by code. The only time it's required by code is if you happen to live somewhere that's adopted 90.1 2010 and later as your code. So eventually, Indiana, it'll be required by code because Indiana follows ASHRAE instead of IECC, but they're still in a 2007 version. So the correct answer should have been false, but because of the way I worded it, I didn't say where. I guess technically everybody could still kind of be correct. So I won't blame you guys for that one. I'll get that corrected on the PDH thing. All right, let's talk about capacity control a little bit here. Oops. And then I'll come back to the final questions here. So there's different ways we can control the compression capacity of the system. And sometimes these are easy to do, sometimes they're not. Sometimes it just depends on the system that you have. The first thing to recognize is that we don't spend a lot of time at full load, right? So HVAC equipment, by definition, its rated capacity, if you will, is based on a 95-degree day outside. A design day in Chicago is 91, right, for O'Hare Airport anyway. Right, so we aren't even at design day at 95, let alone most of the days. We have very few hours where it's above 90 degrees, as you can see on this chart. So for the most part, as I told you earlier, full load is irrelevant. Part load is where the action's at. We talked about handling part load ventilation with CO2. We talked about handling part load staging and fan control. Now we need to talk about what are our choices on part load compression control. I think it's a little bit harder here. It'd be a lot easier if my mouse would let me click to the next slide. All right, so start off basic. The most basic scenario is you have a single compressor and it's an on-off compressor. You get a call from the thermostat that wants cooling, you bang it on. The thermostat doesn't want cooling, you bang it off. This is obviously not the most efficient way to control it, and it's certainly the worst way for dehumidification. If you can get multiple stages, you can do much better. Right? If I can run one compressor instead of two, it's going to be a much better energy operating point for me. I'm going to get a much longer cycle because I won't satisfy the thermostat as quickly. I'll have milder discharge air temperature. I will improve my humidity control because my evaporator coil will be wet longer because I'll be running longer cycles because I'm trying to satisfy them with one compressor. So if you can get 2 or 3 stages on a rooftop unit, you're in usually pretty good shape. There's very few cases you want to use a single stage unit. In fact, the only time I would ever tell you to use a single stage unit is basically you got a big open area like a Walmart or whatever, and you want to use a bunch of rooftops and let them stage with each other. So the system still is sort of staged, even though the individual units have one. maybe you can get away with it there, or a big warehouse or something like that. But anytime it's one rooftop going to one particular area, I think you want to try to get 2 stages if at all possible. Depending on the type of compressor you have, there may be things you can do to retrofit it. Now, we don't use a lot of reciprocating compressors anymore. In fact, we don't use them at all. But there are still lots of them out there in the field on larger units. Reciprocating compressor can have unloaders added to it in order to give it staging capacity. This is extremely easy to retrofit. Basically, if you want to think of it like a V6 engine in your car, right? You got 3 cylinders on each side. The 2 cylinders in the front kind of work together. One goes up while one goes down. The 2 middle ones, one goes up, one goes down, and then the back 2, one goes up and one goes down. Basically, you can put unloaders on these and drop them off in banks of 2. So if you got a 6-cylinder compressor, you can drop off 1/3 of the capacity with the unloader, and then you could drop off 2/3 of the capacity, right? Or you can shut it all the way off. You can make one compressor basically into a 3-stage compressor. So with one compressor machine, you can easily have 3 stages. A 2-compressor machine can easily be 6 stages. And then I got lots of capacity control. If I have a constant volume system, and a stage air volume system would count as constant volume also. If I have a constant volume system, I can use pressure unloaders, which are the easiest ones to install and control. As refrigerant pressure changes, we can unload the compressor, and the refrigerant pressure is based on the evaporator load, so the load of the space. However, if I want to do VAV systems, true VAV, which means discharge air control, where I want to maintain 55-degree air in the duct all the time, I cannot use pressure unloaders. I have to use electric unloaders. Pressure unloaders do not react quickly enough, and the control system will fight the pressure unloader, and basically you'll end up with a 1-stage unit anyway. So you have to use electric unloaders and let the DDC controls do the downstaging of the unit. We don't really see a lot of recips anymore, so we'll kind of skip that, or not skip it, but continue on. The next thing you can do is hot gas bypass, HGB, or HGBY, some might write it. This is really good for humidity control, and that's the main reason of it. But basically, if you follow the piping here, what you're really doing with that hot gas, let's see if I can get my little spotlight thing out. What I'm doing is taking some of the hot gas off the compressor, and instead of sending it over to the condenser, I'm basically stealing it, and I'm injecting it over here in front of the evaporator coil again. Right, to basically falsely load the evaporator. So it thinks the load is bigger than it really is, so it continues to run longer, and hence give me better dehumidification control. I need that long run cycle to keep the evaporator wet, to keep dehumidifying. So basically I'm falsely loading the compressor. It is not an energy saving thing in any way whatsoever. In fact, it probably is more harmful for energy, but it does a really good job of capacity control and humidity control for me. We typically don't just have a 1-compressor machine with hot gas bypass. Usually it's when we have 2 or 3 and we want yet another stage, if you will. We'll add hot gas bypass to it, get a little bit even more staging out of it. It is possible to retrofit hot gas bypass, and obviously you can just do it. But there is a manufacturer out there called RAL that makes a device they call an APR control, which is basically a version, as you can see from the piping, a version of hot gas bypass. So if I can try to follow that with the spotlight. Coming off the compressor, you can see here, instead of going to the condenser, they grab some of that air, some of that refrigerant, and run it through their APR device, which ends up injecting it back around into the evaporator again to falsely load the evaporator. All right, so that's really what that's doing. The RAL folks seem they're pretty good about helping you decide what sizes to use and that kind of thing. And they do claim, and I'm not sure how good the claims are, but they claim it used 12% less energy than just regular hot gas bypass, which is better, I guess. It's easy to retrofit this, and it does improve humidity control. The next choice we might have is a digital scroll compressor. There's a manufacturer, Copeland, that makes these digital scrolls. And the way a digital scroll compressor basically works, I wish I should put the video on here. Basically what it does is, so the scroll compressor has 2 swirls like kind of intertwined. If you ever looked at the inside of a scroll, let's see if I can draw it on here because I'm a really great artist, right? I might have this swirl like that, and then I have another one that's swirled like the other way, and those 2 things set into each other. And then as they swirl, they compress the refrigerant into the eye. So that's basically how those guys are working. So the way the digital scroll works is it literally lifts the top part up, the top head of that guy up, so I'm no longer doing any actual work on the refrigerant, and then I put them back together, and I compress, and I lift it up, and I don't compress, then I compress, and I'm basically lifting it up, putting it down, lifting it up, putting it down, lifting it up, putting it down. The speed at which I put it up and down that allow it to compress dictates my actual capacity. So I'm basically unloading it, loading it, unloading it, loading it, unloading it, unloading it. And I can let it run for numerous seconds at a crack. I can go up and down real quick. The pace at which I do it determines my capacity. It's really good for capacity control. It's really good for dehumidification. You can throttle it all the way down to 10% of its capacity. And if you have two compressors, one with digital scroll and one without, and they're equally sized, now I can go down to 5% of the system capacity because it's 10% on the one compressor. Theoretically, you could retrofit it, but it's not easy, and you'd be designing it on your own. Nobody I know of makes any type of retrofit kit or anything like that. So you kind of would be on your own to do it. The good news is that if you buy it on a new rooftop unit or condensing unit or anything like that, you get a pretty good energy savings compared to hot gas bypass, right? So on that chart on there, hot gas bypass is that red line going across the top. Hot gas bypass does not save you any energy whatsoever compared to on-off compression. The blue line is my digital scroll, and as you can see, my power reduces as my capacity reduces as well. And it's fairly linear, almost linear. It's a little bit curved, but almost linear. The last way to do it is what we're kind of getting towards nowadays. I've been doing this a lot on residential units, and VRF, and I'm sure the commercial rooftop guys will come around eventually as well. But putting variable speed inverters on the compressor is kind of the next thing. Now, that being said, you typically cannot modulate quite as low as you can with a digital scroll. Instead of going down to 10%, you can only go down to 20%. And that's typically because you need a certain amount of refrigerant flow to cool the compressor. By reducing the flow, you risk that you overheat it, so you got to have that flow, just like we do for minimum flows on fans or minimum flows on pumps or air compressors for that matter. It's really good on humidity control as well. It can be used on different types of scroll compression types. Pretty much anything that spins, right? So scrolls, rotary screw, centrifugal, all have different types of variable speed drives you can put on them. We do it a lot on screw and centrifugal chillers, and now we're starting to do it residentially on rotary compressors. So it's only a matter of time before the commercial guys. Actually, we do it residentially on scrolls too. I'm sure the commercial guys will come around to this. It is also, like digital scroll, not easy to retrofit at all, and you'd be sort of on your own in doing it, so you're probably not going to do that. But if you're buying new equipment and you have the option to get either a digital scroll or a variable speed compressor, it might be worth it for capacity control purposes and energy savings. So final thoughts, I mentioned before, like with the Honeywell software, it's nice to have all the savings represented in one place, because then my savings for my DCV and my thermostat and my ERV and my staged air volume don't all add up. Right? If I did calcs on each one individually and added them up, it would tell me I'm going to save 105%. Obviously, I can't save 105%, right? So I have to take into account the interaction of these different things. So here's that same software tool, and this is kind of a lights out example. So in this case, I have a 10-ton system again, same utility rates as before. I have a 15-year-old R22 unit that's ready to be replaced. Back at that time, those units were 8.7 ER, single stage, 80% efficient on the heat exchanger, 3.7 brake horsepower on the fan, single speed. I'm going to replace it with the top of the line unit I can find, right, which in this case is a Carrier 48 LC unit. It's 13 ER. It's 3 stages of cooling instead of 1. It's 82% instead of 80 on the heat. Whoopee, right? But not a lot you can do on heat in a rooftop. It's 3-stage fan instead of 2-stage fan because it does have a little DDC controller in there. I've added the economizer and ERV and CO2. Basically, I put everything we talked about on there today on one unit. Now, in practice, you probably wouldn't put everything on one unit, but in concept, right? So what that ends up saving is over 5 years, $8,000. Annually, that's $1,700, which is 62% energy savings if I put everything on there. As you can see, a good chunk of that, $800, is coming from the indoor fan speed control, almost $600 from the cooling system, and $275 from the heating system. Right, and a lot of that cooling and heating savings is actually coming off the CO2 sensor. So it just gives you kind of an example of that kind of thing that you can kind of see where it's at. There's lots of other stuff we can do. We can interlock a rooftop occupancy to motion sensors. We have thermostats that have light sensors on them. The lights are on, the stat's occupied, the lights are off, stat's unoccupied. All kinds of stuff we can do to integrate these units with control systems so they run at the right time. You can also put them on a full building automation system, get the floor plan graphics, the historical trending, all that kind of good stuff. I'm a big fan of right-sizing equipment, but I don't have time to nag that topic today. I'm sure most of you have been to other classes and webinars where I've nagged it, so I'll leave it alone for today. Just start sizing your rooftops, fans, chillers, boilers, furnaces, condensing units, and everything else smaller than what you normally do, because right now everything's oversized. That's kind of the summary of that. We want to save a lot of energy and improve humidity and all that great stuff, but what I don't want to do is make occupants unhappy, right? On the left, you guys have all seen this kind of chart. The blue is the original construction cost of the building. The purple is the energy costs. The pink is the maintenance costs. But when I add the people costs, the salaries and everything in red on the right-hand graph, all that other stuff smushes down to a little wedge. People are the most expensive thing in a building. If you do stuff to make them uncomfortable, they will spend the rest of their day finding ways to get comfortable again. And that means electric space heaters, jerry-rigging thermostats, lighting campfires in the garbage can at the office, whatever they got to do. So you want to make as much energy savings as possible without anybody knowing you really were there. I have all kinds of studies and data that I can give anyone who wants it. I'd be happy to share it with you. I don't have time to go through all of them today, obviously, but I have just pages and pages and pages, thousands of pages of studies. So if you're interested in something specific, let me know, and I'll see if I can find a study to support whatever I told you. And hopefully I told you the truth. ASHRAE standards, you guys know how to get a hold of those. Codes, you know how to get a hold of those. This one I do want to mention, which is the advanced RTU campaign. If you've not been there, check it out. We don't have time to talk about it today, but it's advancedrtu.org. They have free calculators on there. They have awards for buildings for saving energy with rooftop units and stuff like that. They do some webinars every once in a while. So they got good stuff there. Advanced ASHRAE design guides are free. ASHRAE.org/AEDG, Advanced Energy Design Guides. I think we are now up to 11 of these books for different types of markets, schools, offices, retail, etc. They basically give you a couple pages on all the stuff you should just do prescriptively to save 30 to 50% energy over the old standards that at the time the building was built. And one of the things they always mention is CO2 sensors. It's always in there because it's super easy to do. Duct sealing's typically on there, economizers, improved efficiency of the refrigeration systems, things like that. Add insulation to the building, improve the lights, etc., etc. All right. We do not have any more poll questions, so if you are needing to drop off and leave, that's totally fine. The only other poll question is the one that basically says, am I an idiot or not, which you're more than happy to answer, but you're not required to do that for PDHs. I'm going to read the last few questions that you guys typed in to see if there's anything else I can try to help answer. All right, so let's see. Joe typed in, if I have staged gas heating, can I do staged airflow in heating mode? In concept, the answer would be yes. In practice, you cannot do it on a standard unit because you don't have any way to change the economizer positions as you change the airflows, because the economizer can only handle 2 stages of airflow. Additionally, most of the manufacturers have not yet published data on how much airflow they expect for each individual stage of heating. So yes, you can do it in concept. Maybe if you have a VAV unit and you want to use it as a staged air volume application, you might be better off doing that. But generally speaking, the manufacturers aren't comfortable and ready to do it yet, but in concept, yes. Joe also asks, are the factory program VFD set points field adjustable? Yes, the VFDs can be adjusted from these manufacturers in the field if you need to. Generally, you don't, because there's not much you can do differently. But let's say they set it at 67% and you really felt you needed to have it at 69%, you could go in there and change that. Obviously, you can't go less than the CFM that is required for the cooling capacity, which generally needs to see about 350, 400 CFM a ton or so. Joe asks if carrier rooftops use the Honeywell W7220, which is that jade economizer. All the units that have staged air volume do, well, the non-DDC units that have staged air volume have that jade economizer standard. Other units still have the old Honeywell economizer, but you can take an option for the jade if you want it. And then once they run out of inventory of their old Honeywell parts, then they'll have to make everything be jade. And then the ones that have DDC do not use it. They typically just have a Belimo motor on there, and the DDC circuit board drives the motor directly without having an economizer controller that's separate. Cliff asks, why use SAV rather than VAV? Does it cost less? Really, it has nothing to do with cost. It has to do with control. A VAV unit, to change his airflow, has to look at a pressure sensor in the duct. If nothing is changing in your duct system to change the pressure, the VAV unit will never slow down. So a VAV system only works if you have VAV zone dampers out in the duct. If you don't, Nothing changes the pressure, hence it doesn't see anything, hence the VFD never slows down. Staged air volume is a way to change the speed of the fan for systems that don't have zoning on them. So we look at the cooling and heating stages, mainly the cooling stages, decide if we can slow the fan down there. So no, it's not a cost-saving thing. It's a control mechanism. You don't have any way to control a VAV system, a true VAV system, which is a zone damper system, if you don't have zone dampers. Joe asks, whose VFD does Carrier use? It depends on the equipment, but a lot of the equipment has ABB drives in it. That's pretty common on a lot of the Carrier units. Some of the older ones, like the ones you have on some of your halls there in your building, Joe, have what was it? I think it was Toshiba drives on yours. Let's see. Boris asks, would you suggest a VFD to reduce the CF from a small hood exhaust fan when the sash is closed? I don't really know the answer to that, because that sounds like when you say a small hood exhaust fan, I'm thinking some kind of process thing going on, so I don't want to answer that directly. However, when you say small, I think don't spend money on a VFD. I don't know how small is to you, Boris, but if things are small, probably not going to be worth the effort of retrofitting a bunch of stuff on them. I would find the big fans in the building and target those first. But I don't know the answer to your specific question about the laboratory hood you're talking about. Joe asks if the 48 LC Carrier unit is available in a 27.5 ton size. I don't know, Joe. That's a good question. I don't think it goes quite that high, but we can open up that software I was just using, and that'd be the fastest way to see that, I think. Let's see. I can do that real quick without much pain. Looks like 25 tons is the biggest size, Joe, to answer your question. All right, it looks like all the questions. If anybody else has any other questions, just go ahead and email them to me or call me. I'll put my email back on the screen for anybody who's still hanging out. And we'll see you guys next week or the week after, depending on when you join us next. Thank you for your time.